Okay, we'll get started. Good afternoon, everyone. My name is Gaiman Yi. I'm the Technical Director of the i4energy Center. Welcome to today's i4energy seminar. Today's last one of the semester, so unfortunately, starting next Friday, we'll have to go find our own lunches. We'll start off again. We're gonna have no seminars during the summer, and we'll start up again in the fall semester. So just keep an eye on the announcements when we get started again. So also want to welcome those that are viewing today's seminar on the internet. So let me introduce today's speaker. It's Gerardo Diaz. He is an assistant professor in the School of Engineering at UC Merced. His research interests include energy conversion systems, dynamic simulation and control of thermal systems, adaptive thermal networks, absorption chillers and heat pumps, vapor compression systems with alternate refrigerants, microchannel heat exchangers, and artificial neural networks and genetic algorithms for optimization of thermal components. Professor Diaz has a mechanical engineering degree from the Universidad de Santiago de Chile and MS and PhD degrees in mechanical engineering from the University of Notre Dame. Let's give a good welcome to Professor Diaz.
All right. Well, it's a pleasure to be here. Thanks for the invitation. It's always nice to get out from a little dry type of weather that we have there in Merced. But it's a very nice time to basically talk about an important topic, and you can look at it from the perspective of we're going to be talking about waste, so why would we talk about that? Not very interesting. Or you can look at it from the perspective of what can we do with that. And I think that's the type of motivation that I want to do. So many of the results and values that I'm going to be showing are related to the campus in Merced, but they can be extrapolated to other type of communities or even like city-scale type of applications. So let's look a little bit about waste. So if you look at it from the perspective of what we think about waste, is basically those materials that are of little or no value to humans, right? We want to get rid of that. We don't want to have it. And this is a perfect example. You probably don't remember, but in 1987, there was this barge that was the Marlboro 4000 that had 3,100 tons of waste. And somebody basically came up with the idea or with the question if it had medical waste on it. So suddenly people said, no, we don't want that being dumped where we are. So they didn't allow this barge to docked anywhere. So it basically ended up going to 6 different states where it was not received, and 2 different Caribbean countries where it was not received, and eventually had to go back to Islip, New York, where they basically had to incinerate it. So again, when we look at the perspective of waste in that way, then we say this is kind of like a major problem that we don't want to have to deal with, right? Now, look at it from the reality of other places in the world, in other countries. What is waste for some people might actually be the way of life of other ones, right? There's some people that get cardboard or get their food. They basically can sell some of the things that they find there. So we have to put it in perspective. Now, imagine if you look at it from the health point of view, this also reminded that you have people basically living in those conditions, right? So can we do something about it? Can we do something that is a little bit better than that? Even in places where you don't have to live out of the landfill, there's still, I mean, is there any waste management in some places? I mean, the trash accumulates there. There's rats. There's all sorts of health problems. Even in places you can see here, it doesn't look so underdeveloped, right? But it takes a certain, when you tell a certain community, well, you have to pick up the trash, what is the incentive? Well, yeah, the health of the community, the people might get mad at the mayor or anything, but at the end it's a cost, and you have to justify to keep the cities clean, right? So again, from that perspective, we have to also look at it at what are the different types of waste that we have to deal with. So it's not just a matter of sending your trash and all the things that you don't want to a landfill and basically get rid of that. We have basically the municipal solid waste, that is basically what is collected by the waste management trucks. But also you have a hazardous waste. You cannot just basically put them in your trash, or you have industrial waste, agricultural. Now, again, we have to differentiate. There's some types of waste in which we can actually do something about that. For instance, let's take a look at this meal that I just had. So we have a burrito. It's wrapped in a paper. It's wrapped in a tin foil. I need a napkin, and then there's like a cardboard type of a plate there. If I want to have a fork, then more waste, right? So if you look at the packaging waste, it has been increasing significantly. In fact, the most developed countries, you see a huge spike in packaging waste, and again, it's because of this type of situation. But again, let's say, well, we can recycle that, but if it has food, for instance, so it is contaminated. You cannot recycle that. So what do we do with that? And we just send it to the landfill, right? Or we incinerate it, but incineration is not very good. So again, so maybe we could do something about this part. Maybe we can reduce the packaging in the amount of food that we eat or things like that. So I'm not going to eat maybe 1/3 of my burrito, so there's part of the food that also gets wasted, right? So maybe portion control. There's maybe, yes?
Actually, all of it except the tinfoil is compostable.
Yeah. I mean, there's certain possibilities that you have, but there's other things that, for instance, if you have one of those biodegradable spoons, they're supposed to be biodegradable, but if you look at what the composting people are saying, they're saying they don't compost very well. So we have to basically look very well at which works and which doesn't work, what can be recycled, what cannot be recycled. So composting is a good part that we have to consider. But then there's other type of waste that come out of a byproduct of a process. So if you have agriculture, then you're going to have certain products that are not suitable basically for selling or things like that. So you're going to end up with some certain quantity that is not you basically have to compost it, or it's just basically waste. But again, you have radioactive waste, very unfortunately. During these days, we have been talking about that quite a bit with Japan, construction, demolition, mining, and universal. And for instance, again, things like these light bulbs that you have there, they're extremely efficient, so you are saving a lot in terms of reducing the amount of power that you need in order to have light in a room. But also you have to make sure that you dispose them properly because they have mercury, right? So if we are going to be using that for reducing the amount of energy that we consume, then we also have to be careful when we dispose them so that we don't create an environmental problem, right? Okay, so let's look a little bit at some of the statistics of waste in the US. And I was mentioning, look at the level of development of a country and the amount of waste that is being produced. So for instance, again, you have Luxembourg, Denmark, the US, Norway, and Ireland heading basically in terms of the amount of waste. So this is kilograms per capita. The white one is household waste, and the dark one is municipal waste. So again, it's something that it tells you something like this, right? The fact that we eat our food and we have a lot of packaging, we have a lot of things that are added, right? If we look at from the perspective of per capita, kilograms per person per day, so that would be the red line here, and the total waste in million tons, the blue one, we're going to see that in general over the years it has been growing, right? But then it's slowly starting to go down. So it's the trend that we want to do. I mean, we certainly don't want to increase in a certain rate of the population, which we're going maybe 1.6, growing 1.6% a year or something, and we continue to grow the population of the world, and we continue to generate more and more waste. And if the amount of waste is growing faster than the rate that the population is growing, then we're heading the wrong direction, right? Now, I was mentioning about the packaging, right? So if you look at a little bit of the breakdown of the types of waste that we find, so paper or cardboard, things like that, is very, very high, 28%. Food scraps, so again, maybe portion controls, things like that. Yard trimming, so again, can we reduce the yard trimming? Yeah, maybe you can mulch or things like that, but sometimes you need to basically remove those yard trimming. So again, there's some wastes that you can actually reduce, and some other ones it's just a byproduct of the operation. If you are in an industrial setup, there's going to have certain byproducts, especially, for instance, in the wine companies or like the dairies or things. There's certain byproducts that is part of the operation. So if you want to operate, you're going to have that waste. Let's look at California. So in California, again, you have mainly 3 commercial, residential, and self-hold here. In terms of the material classes, see again, paper and cardboard and things like that, 17%. So the packaging, again, is been growing quite a bit, and that is something that maybe we can do something about. But then again, you have other sources, other organics and inerts and things that are that compose the total of the waste that is being produced. And if you see food here, we have about 15% of the food that basically becomes waste. So again, there's something that we can do in that way. In terms of agricultural waste, there's a nice work by Professor Norbeck there in UC Riverside. And you can pretty much see the location where you have most of the waste being generated here in California. So if you're looking for the forestry type of waste, the forest, not only by the natural decay of trees and everything, but also because of the industry, lumber and things like that, then you're going to find that concentrated in the north of California here, right? Then if you look at agriculture, then Merced, for instance, where we are, would be a big one, and all this region here of the Central Valley would be significant. And also here we can see the Monterey County being important. So that's where agriculture, and again, many of the waste that you find there is just basically that comes out of the operation of the agricultural places. So it's not that you can go and reduce it significantly. And then MSW, yeah, maybe MSW, that is a municipal solid waste, we could do a little bit more in order to reduce, but that's mainly located in the south here, right? We have maybe one county here, but in general it's in the Los Angeles area, right? That's where you find most of it. So what are some of the traditional waste management techniques? Land disposal, again, they have been changing over time. Initially, which is basically dumped to the sea, then that was banned. Then basically land disposed on the land, and then that is being banned. Now, land disposal has to be very controlled, but you still have maybe possibility of having, like, say, groundwater contamination or odors or things like that. You need to make sure that that gets covered. Then you have the sanitary landfill that is basically an ultimate controller, but there's not many places that are available for, in the U.S. especially, for these locations of these sanitary landfills. Solid waste incineration, again, this was big maybe 50 years ago. It's still being done, but the problem with incineration is that you are going to have some emissions of VOCs or some other gases that are basically volatile organic compounds or other gases that are basically poisonous, or they can even have effects of cancer in the population, right? So again, we have to be able to do something about that. And then recycling, reuse, and composting, those are things that are going in the right direction. What other less traditional methods are out there? One of the possibilities is gasification. Okay, so and again, when I say gasification, it's not incineration. Incineration, basically, you are putting all the oxygen that you need. In gasification, you're using different agents. You can use air as a gasifying agent, but in general, you are using a lot less oxygen for basically gasifying the waste. So what are the different types of, the most common types of gasification that you have? Here you have, for instance, a conventional gasification. So you have a certain amount of waste, for instance, I don't know, it could be wood chips or biomass or anything like that. And you're going to add a certain amount of oxygen, which is not stoichiometric, so you are not combusting again. And then you go through the reaction, and you end up with carbon monoxide and hydrogen. Now, you would say, well, carbon monoxide is, again, a poisonous gas, so why would we want to do that? Well, but still it's a fuel, right? So it's different than, say, CO2, where you cannot, it's not really a fuel. So the conventional gasification, you could be basically running something like a downdraft gasifier with this, and you're going to be able to convert some of your waste that is here with a limited amount of oxygen into carbon monoxide and hydrogen. Other types of gasification, well, instead of using, for instance, air, then you use steam, okay? And it happens to work out very, very well. So you have your carbonaceous type of waste, you add steam, and then you're also generating CO and so carbon monoxide and hydrogen. So here we have to start seeing which one is more efficient, which one makes more sense. In one, you have air, but the problem here, notice that if we are going to use pure oxygen, then this works out very well. But air has nitrogen, and quite a bit of nitrogen in it. So we have to consider that there's also going to be a certain, quite a bit of nitrogen that is going to come out in the syngas composition. So we're going to see that later. But that is an aspect that we have to consider. Here, again, steam gasification, the purpose, again, is to basically end up with a fuel. So you're going to end up with that. Hydrogasification, if you were to use hydrogen, basically, you would basically obtain methane from that. There's other components, right? But this is the main type of reaction that you would have. And then, again, in Riverside, they have the hydrogasification, which you have your carbonaceous waste, you add steam, and then you add hydrogen too. You'll see it there. And you break it into this. Now, again, there's several reactions that are happening at the same time, but those are mainly the reactions that you're looking at. So the idea would be, well, we can compare these. There's a lot of people working in each one of these versions of the gasification, but the idea is to break the molecules that you have in the biomass or in the municipal solid waste or anything, and transform them into lower molar weight type of components, again, like CO or hydrogen or CH4. So let's look a little bit at UC Merced. So the title there said, how do we use waste and how do we try to address the issue of going towards zero landfill waste and also net zero energy in a campus that is starting, basically. It's only been operating since 2005, right? So not much of a history of use of waste or use of renewable energies. But on the opposite, you can look at it, you have all the potential to apply the techniques that are available now in order to grow in a very sustainable way, right? So one of the things that you see here, this is the campus, and this is when they were building the 1 megawatt solar farm that they called there, the solar panels basically. So this provides a substantial part of the energy that is basically consumed in the campus. It's about 20% over the whole year, but at certain times of the years, at peak times, you might be looking at maybe 70 or 75% of the energy of the campus being provided by the solar energy. Now, here you see a tank, and that turns out to be crucial because that tank there is a 2 million gallon chilled water tank. And what the campus does is basically it chills the water during the night using vapor compression systems. And then during the day, when it's hot, it circulates the water through the cooling system, and that's what basically that's the air conditioning of the room. So you shift the high load of the chillers basically to the night when it's cheaper, and then during the day you basically circulate that chilled water. But if you have now, for instance, renewable energy, does it make more sense to chill during the day when you're basically getting the energy from the solar panels or not? So there's a study, there's an optimization there, depending on the amount of energy that we're getting, the energy that we need, and how much is the cost. And also operations, for instance, if you are trying to run your cooling towers during the summer, they're less efficient than, say, during the day. In the summer, they're going to be less efficient than during the night. So again, there's an issue of efficiency of the equipment that is being used for cooling. Right. So this project sits into a study that's been funded by the California Energy Commission, and it basically looks at 3 different parts of the puzzle. And why do we have this? Because it's 3 different resources that we have at Merced. One is looking at the energy efficiency of the campus, of the buildings in the campus as a resource. So if we have more efficient buildings, then we use less energy. We need less energy. Then the other part is solar energy here, which is abundant, especially during the summer. But then we have to see what happens during the winter when there's fluctuations. So we have that resources, solar energy. And then waste. So in particular, we're looking at plasma gasification of waste. But the idea is that this is a dispatchable type of resource. I can decide when I process my waste. I cannot do that with the solar, even though you can predict pretty well how much solar resource you're going to have. But you get what you get, basically. If you have the resource, you're going to be able to produce, but you cannot decide when you're going to be producing with solar energy. That's not the case of the gasification, the plasma gasification, right? So this is what I was telling you. This is the loads of the campus and how much energy is being generated. So right now we have a 1 megawatt solar system. So that would be this green line that you see here, okay? Now, we have scaled that to see what happens if we had 2 megawatts or if we had 3 megawatts, and we can scale it even more. But that's kind of like to give you an idea. These dashed lines here are projected lines of what we would tend to get in summer with a system like that. And these are the loads. So remember I told you that we chill the water at night. So the chillers are basically running at night, and that's when you get the big load on the campus. It's, again, maybe 3 megawatts there. And roughly it's turned on roughly like at 10 p.m. It goes up. It stays chilling during the night when the rates, again, are low. And then it goes down. The chillers are off now. And now you have the normal operation of the campus during the day. Now, if you see during the summer, for the normal operation of the campus, you see that probably 75% is covered by the solar array. Okay, so California is trying to go to like 20% RPS, so renewable energy portfolio, or even to 33%. Now here we're in certain occasions 75%. So how do you deal when you have a high fluctuation, large fluctuation of your resource in this case? So that's for summer. We can predict the summer pretty well because it's very consistent. But what happens in winter? Okay, now in winters, you still have the loads due to the chiller. Now they're a little bit lower with respect to summer. And here's the regular operation of the campus. But now your resource is a lot smaller. So this is the 1 megawatt, this is the real one, this is the 1 megawatt array. But if we had 2 or if we had 3 megawatts, then again, by just scaling output of the 1 megawatt, this is what would happen. So if you have a situation like this, then maybe you could be shifting some of your loads of the night basically to the day, because say if you have a 3 megawatt solar array, you could be covering part of that load with your solar array. So, but now you see you have a very sharp drop at this point. It goes up, it goes down. So that fluctuation that you have there, what if we use, for instance, the waste to smooth that out? I mean, if we can predict the availability of solar resource 15 minutes ahead or an hour ahead, then we could basically say, okay, well, let's have the storage as the waste, and basically we decide whenever we want to use the storage, right? So it's an optimization problem. When is the best way to use the resources that you have? Okay, so let's look at the idea of trying to go to zero net energy. So we have been working quite a bit with facilities here and at the campus, with especially John Elliott, the manager for energy. And here you have basically the analysis of what it would take to go to zero net energy in a campus that is growing. So right now we have about, I don't know, 4,000 students. We have to get to 25,000 students maybe in 30 years, right? So, so the idea would be, if we have business as usual, then this would be the loads that we would be using. And this is, again, this is the amount of energy that is needed by the campus. And it's not only the power, it also includes the natural gas that is used. And there's a little fraction there of gasoline or diesel for the trucks that we have there, or the fleet, right? So the idea would be, if we were to just stay the way that normal buildings and operation of a campus is, then you have to basically produce that much energy, right? 2036 here. Now, if you look at the resource of energy efficiency from the buildings, you can substantially reduce that by basically 62%. Okay, so that would be, again, the blue is building efficiency established targets, and then the green one is building efficiency stretch targets. So initially we were building to use maybe 50% of a benchmark building. Now let's design buildings to use 25%, and then maybe let's push it all the way to try to have a building that either receives all the energy from the solar panels or self-generates some of the energy that it uses. And on top of that, being very efficient. Then we have the solar resource here that is about 24% that could be covered. One is by centralized solar generation, again, in terms of like a solar array, or distributed solar generation, which you could have in the actual buildings generation in a distributed manner. And then if you see this point, so when you get to zero, that's when you reach zero net energy. So that tells you that you don't reach zero net energy. So you need something else to basically accomplish that. So we're hoping, and we're basically doing the analysis to see if you can cover that with waste. Or again, there could be some other addition there. There's really not much hydro there, and there's really not much wind resource. But again, I mean, the idea would be, if you can pretty much minimize the number of resources, but you can do a very nice optimization of when to use them, then that would help quite a bit in actually reaching that goal. So again, I was mentioning that doesn't cover only the electric generation, it also covers the natural gas consumption. So if you look at the natural gas consumption in terms, obviously there's a cost involved here. They charge you a lot more in winter and a lot less during the summer. But this is the amount of energy that basically you require to run basically the campus. Now here, again, we've used, so every time that we get a new month, for instance, if we get this month when we finish April, we're going to replace the 2010 data that was used to generate this plot, and we're going to have the 2011, and then we continue to replace with the latest information that we have, right? So we can track the generation of waste on campus fairly well, and again, we can look at not only the solid waste, but also we can look at other wastes, like for instance sewage, or we have operations of cooling towers, so there's a blowdown of the cooling towers, or we have the reverse osmosis reject, that this solid waste is not something that you can basically reduce. This is for the operation of the campus. So you have that, or you have the boilers, where you have the blowdown from the boilers too, and we can basically track that over the years and provide some estimates of how that's going to be in the near future or even medium-term future. So we can basically look at those aspects. But something that is important is that we're going to be growing as a campus, and it's going to be basically from 4,000 students that we have right now up to like 25,000. So what's going to happen with the waste at that point? So common sense is going to tell you that the waste is going to go up. But the important thing is waste per capita. You want the waste per capita to go in the decreasing direction instead of the increasing direction. So even though the waste, the total amount of waste is going up, or maybe at a different slopes. So that's basically what you're seeing here. From 2006, 2007, 2009, it was kind of going up. It went up quite a bit, and quite a bit of this is because of construction. Remember, it's a small campus, so if you build a building, and in fact we had one management building that is being constructed, and we had the dorms being constructed, so that affects quite a bit. But a lot of that can be actually recycled, so that's not so important. That can be basically diverted. The important one is the one that goes to disposal, so the one that goes to the landfill. And if you see, it was growing, and now it's kind of stable. More than likely what's going to happen is it's going to keep growing. The thing is how fast it grows with respect to the number of students that we get. But if you look at it in terms of per capita, is that tons of disposed waste per capita, it is going in the right direction. Basically, as we add students, then we're not generating as much waste as the number of students that we're getting. So it has to go in that direction. So again, roughly to have an idea of the numbers, the total waste produced is about 1,200 tons. 300 of that, 300 tons are going to landfill, and total recycling, composting, and things like that are almost 900 tons. So these two numbers are important. The 300 one, that's the one that is right now is going to landfill, and how much is the total waste that we are generating. So we talked about the types of waste that we have on campus. So let's go and analyze that waste. So we looked at the arrow reject, the reverse osmosis reject, and we analyzed the composition of that. We looked at the boilers. You have the boilers right there, so the boilers blow down. All these ones, again, they're just waste that is generated. This is the cooling towers, what comes out of that. All the salts and things like that, so it's concentrated with salts. And the sewage here, right? So let's take that and analyze that. So what we're looking for is two things. We want to have a certain amount of organic carbon on that waste, liquid waste, but also we want to have conductivity. Because why do we want conductivity? Because we're going to run electric current through that system in a closed discharge type of mode. So the higher the conductivity, the better to basically move to basically have a current through that. So we looked at the numbers here, conductivity is here. Boiler is 699, central plant 411, again, depends on the units that you're looking at. So it looked like the sewer, what came out of the sewer is basically the highest one. But then you have boiler and arrow reject being second, very close to each other, and the central, the cooling towers, that has the lowest conductivity. So if we were going to use some sort of liquid waste in a particular mode, and we're interested in conductivity, then you would select either the sewage that was coming from the sewage, or the boiler, and potentially the aero reject. But it's also going to depend how much you're producing of that. Obviously, the sewage is the one that is the most abundant. Let's look now at solid waste. Again, we were mentioning we have a lot of packaging that it's used in order for us to eat, right? So we have containers, we have cans, we have basically plastic wraps and cardboard. And it would be interesting to have an idea of how much energy is in this type of wrappings that we tend to use, right? So let's see. So again, we went for an analysis of these components that are very common. These are, again, this is what you see every day people eating, right? So we analyzed, for instance, here I have just a list of, I think I have 8 here, but we have been adding more. But look at the amount of carbon, for instance, in some of those. So this is the naked bottle here, the amount of carbon present there. And look at the heating values of these components here. For instance, let's look at this one. There is the to-go bowl. That is in kilojoules per kilogram. If you convert that to roughly like calories, like would you use like nutritional calories for the ones that you see in the labels of things, that turns out to be about, let's see, the to-go bowl is about 8 calories per gram. If you multiply that by like 45 grams, then you have like 380 or 400 calories of a container. So if you're eating a 400-calorie meal, do you need a 400-calorie container to have it? Or can we do a lot better than that, right? So if you look at other components here, again, look at that naked butter. It's huge amount of energy there. But a lot of this can be recycled. So I think the main point is not to go out of this talk thinking, oh, let's go and try to gasify everything. No, let's try to do as much recycling as we can, minimizing the amount of packaging that we use. Let's do composting. And there's going to be things that you cannot recycle, for instance, if it's contaminated or things like that. So what happens with that nowadays? It goes to the landfill, right? So let's try to do something with that, which happens to be significant. It's a significant amount of energy and waste in terms of quantity that we have. This is what I was mentioning. This spoon says there, I don't know if you can read there, but it says biodegradable. But if you look at the results from people that are doing the composting, they don't compost very well. So what people are going to do is just going to throw it to the trash, and that's going to go to the landfill and stay there for a long time, right? Okay, so let's start. So we mentioned some ways of gasifying waste, right? So let's look at some results of gasification. So let's see this little downdraft gasifier that we have, and let's see how it works. So you have a top that covers this, and these are the openings for the oxygen. So the oxygen basically, or the air basically goes in, and then it gets fed to the gasifier at a certain section, like middle section here, roughly. And right before there's a cone that is basically the reduction zone. So right before that is where you're adding this air. Then you fill this with biomass or what you're going to be gasifying, and then again you put the top on that, and you go through the process. So the syngas basically gets sent through here. It goes through some filters, and then it can be basically utilized for again. You can flare it, you can heat water with that, you can put it in an internal combustion engine, turbine, you can mix it with diesel and run a generator. You can probably try to go and generate biofuels with that. So different options. So the starting procedure, you need that charcoal to basically, especially in the reduction zone, that is the reduction zone is the gasification zone. Then we add biomass from the local landfill. And how are we doing it? Okay. So then that gets added to the system, and then we close the lid, and we basically go through the gasification process. Every time that we run out of fuel, then we open this little lid that we have here, Let me see if I can see it there. And then we add more biomass, and we continue with the process. So there's a drying process of the, you're basically drying the moisture of this biomass. Then you go through a pyrolysis, combustion, where the area where you have the air coming in, and then the reduction. That is really the gasification part. You go through some filters, and then we have a sampling port, so we can actually get a sample of that syngas that is being generated, and then the rest we're just, at this point, we're just basically flaring that. So let's see. Okay. So this gives you roughly the operating conditions that you have inside. So you have several thermocouples there, and then this is right before the reduction zone. So let's look at the green line there. We're very close to 1,000 degrees Celsius, okay? So it basically stays like that. Every time that you see these drops here is when we need to add some biomass to the system. The system can also use an auger. We didn't use an auger in this particular time. And there's another thing that is important is that if your biomass is too small, so it basically breaches, so it in a certain way blocks the path of the air, and then you can also have fluctuations in the flow and in the pressure. So you also see some of that in this and in this run that we were doing, right? So let's look at the results. Okay, so that is basically the flame that you're seeing. Can you see it? How many can you see? How many of you can see a flame there? Yeah. So there's a flame. It's pretty hard to see, right? So it's very easy to think, oh, it's not lit, but it's really a flame there. It's fairly clean, and that's basically the. We're basically flaring the syngas that was produced with the little gasifier. Now compare that to open burning, right? I mean, so that's not what we want to do, even though it still is being done. But we're trying to see what are the ways that we can actually generate energy in a cleaner way, right? So let's analyze the results. So we took our sample, we took it to a gas chromatograph type of system, and we had landfill waste. So again, this is from the landfill. That's the one that I was showing you. And we had two different settings for the flow, high flow and low flow. And you can see that you're basically producing about 10 to 8% of this smaller fraction of hydrogen, CO2 in the 15%, carbon monoxide, which again is useful for generating energy, about 9 CH4, so methane does 2. But look at the amount of nitrogen that it's out there. And we had a little bit of oxygen, so that means that we have maybe too much flow into this in the downdraft gasifier. But basically, you have 15% plus 66 or 60% of nitrogen that is not really a fuel. So all that conversion that you're doing is to obtain a fuel that has very little, a very low heating value of the order of 2.53 megajoules per normalized cubic meter, or 2.10, right? So we said that's not very good. So let's try to look at some other type of fuel. So we basically use a very uniform type of fuel that was Douglas fir wood chips, and they were basically cut with a uniform size, roughly taking in consideration the size of the internal part of the gasifier, and that gives us a lot better results. And if you actually look at the literature, you're going to notice that these numbers are very close to what a lot of people report. So we're looking now at maybe 17% of hydrogen, 20% of carbon monoxide, and 2% of methane. But we still have 50% here of nitrogen and CO2. But the LHV now is much higher. So let's take maybe an average between the two large ones. So maybe that and this one. And let's see some. Okay, so first what we did is we generated a model, and you can see roughly like how the model is predicting the performance of that downdraft gasifier. And then, so it's doing a reasonable job here. And now let's use it with just oxygen. So instead of running the downdraft gasifier with oxygen, with just a pure source of oxygen instead of air, let's run it. So that actually turns out to be much, much better. You see, you go into 40% of hydrogen and much larger with CO2, with CO. But then again, you need a source of oxygen. The same thing if you're running the Douglas fir ones. You get much better syngas quality, but it's. So let's look at the order of magnitude calculation. We need the number of natural gas terms used on campus. 2010, 2011 is roughly 502,000, right? So we convert that to megajoules. If you have the LHV of the natural gas, is roughly 34.6. So that tells you that you need this volume of natural gas in order to supply that demand that we have there. Now, what if we use the syngas that we were generating? So we're taking, again, the average between the two best conditions that we got with the Douglas fir and with the landfill waste. So you can see that when you convert that in terms of volume, you need an order of magnitude more of volume to replace, of syngas, to replace what you had in natural gas. Now, you consider that you get about roughly 2 cubic meters of syngas per hour per kilogram per hour of biomass, then that tells you that you need about almost 7,000 tons of biomass needed. So if you compare that with the number that we said, that it was about 1,200 tons of total waste generated on campus, imagine if all your waste had the composition of this biomass that we use, you would need about almost 6 times the amount of waste to replace the natural gas on campus. It doesn't make any sense, right? So that's not what we want to use. So let's look at other possibilities. So this is under construction. In fact, we were moving the equipment and everything. And we're interested in basically analyzing the gasification process, but using plasma in the process. So we are expecting to basically have this lab running by the summer, hopefully earlier than that. And the idea would be to characterize in quite a bit of detail the compositions and volume dry and the yield that we have of syngas, depending on the type of waste that we're using, with respect to having a process in which we have you basically have two processes in one. One is you're doing the generation of the steam, and then the second one is you have a plasma torch to do the gasification. These are the two power supplies that we're going to be using. Now, when we talk about plasma is very wide, okay? So we can basically look at temperatures of millions of degrees and number densities that are 10 to the 33 particles per cubic meter, but we're not basically looking at something of that sort. We're basically operating somewhere in this region where we have temperatures. Again, it's a non-equilibrium type of plasma, but you are going to have temperatures, I don't know, maybe in the 5,000 to 10,000 degrees for the ionized part, the electrons. But it doesn't mean that the syngas is going to be operating at that point. Only a small fraction is ionized. So basically the equipment that we're using, we can basically add wastewater. We go through this plasma electrolysis type of system here. We generate steam and hydrogen from that. That is basically what is being used as the gasifying agent, where we put the biosolids here, and that generates syngas, which will probably need to be scrubbed if you have any sort of like hydrogen sulfide or anything like that. And then that can go to a prime mover, or you can heat water, you can do things like that. Let's think the movie. So that's the plasma electrolysis. So you're generating steam and hydrogen at that point, and then this is basically where you're going to have the plasma gasification of the biosolids. So that's pretty much what we're going to be using. The company that we're collaborating with is for Plasma Labs for basically making these this system. So when we talk about electrolysis, a lot of people are going to say, well, but that's very inefficient. It is, right? But that's not the point. We're not going to be operating in conventional electrolysis. If you look at the curve of current and voltage, when you start increasing the voltage and you're doing standard conventional electrolysis, you need a lot of current, right? But there's a certain breakdown point in which it becomes very unstable, but you continue to increase the voltage until you get to a stable region where you see the current that we're using is much, much lower. So this is the area where we want to be operating for generating that steam and hydrogen, right? So again, we do our thermodynamic model. So part of the research is actually understanding those processes. The two processes that you saw is looking at the detailed analysis of those two processes, and with respect to the type of waste that we're using, right? But we can do first approximation type of model using basically thermodynamics and the gas kinetics, basically. So the reactions that are basically being considered are mainly these ones that are, again, boudoir reactions. So you might, if you're operating relatively low, you might actually go in the opposite direction, generate some deposits of carbon, but then you also have, so you see this is just mainly with the carbon, and here you have the methane decomposition, then here you have the water gas shift. So we put that into our system of equations, and we have the quantities that are basically constants for equilibrium, and we iterate until we actually get the results. So we have to basically model two parts. We're modeling the first, the generation of the steam and hydrogen, and then we do the gasification part. If you look at that, I'm just going to show here the end results of the syngas. The fraction of hydrogen, so this green one is hydrogen, is much, much larger than what you saw with the downdraft gasifier using air, right? Now, carbon monoxide is also high. It's in the 30%. This one is maybe in the 45%. Now, since we are putting steam, then we're going to have some steam involved there. So what we're going to have to do is basically, if we want to put this into a prime mover, we need to condense this water. Now, a good way of using that condensed water is basically to heat up the water that's going to go for the plasma electrolysis. So we don't have to put that energy to raise the temperature. But also, at the end, you end up with water that could be used for watering the fields, or soccer fields, or anything like that. Or you could even have a second circuit that goes to the toilets, for instance. So it's not potable water, but you can actually use that for the water that doesn't need to be that clean. And then we have CO2 basically going down. All right, the CO2 that is going down as the temperature increases. Now, this is not the temperature of the plasma. I want to make sure that this is basically the temperature of the syngas. The plasma is going to be higher, right? But it gives you an idea that the quality of the syngas that you're going to obtain is much, much better. So if you're looking at, for instance, hot water and steam used in campus, let's only concentrate in the 300 tons that go to the landfill. So if you calculate the LHV of the syngas with this other method, it's much higher than what we had before. It's about almost 11 megajoules per normalized cubic meter, right? So in terms of energy availability, energy that is available there, you convert it to therms, would be almost 61,000 therms, and then you can also convert that as kilowatt hour, right? Now, here is basically what I'm showing in terms of the requirements of steam and hot water for the campus for 2010. And if you look at basically the number of therms that you need for generating steam, is about 81,000. So 61,000, you could pretty much cover 75% of the steam that is actually being obtained with natural gas. Or for hot water, you can maybe do about 20% of that. Now, remember we said 12% in the little wedge chart that we had. So it means that we can do something with this waste. If we were to convert it to electric energy, let's think of a 30% efficiency. And we also need energy to generate the plasma, right? We need some power. So let's consider 50% of the energy generated. So out of the 30% that was obtained, 50% of that goes to generate the plasma, and we end up with this number. So the amount of money in a certain way that you could save, considering an average value, it varies through the year, but if you're looking at to replace the natural gas that is being used to generate steam or hot water, you could basically be saving around 44,000. And if you convert it to electricity, you could be basically saving a little bit less than that. So maybe it makes more sense to use it for, you're going to have higher efficiency too if you use it basically for hot water or for steam, right? The amount that you save for not having to hold that to the landfill is relatively small, but again, it's something, if you extrapolate this to when we have 25,000 students, everything might help a little bit, right? So again, let's look at, this is one of the final things, but let's look at the flow chart of waste that we have. So out of 100% that is produced, delivered, and you have to unpack and prepare, you present to customers, students, or things, faculty, or anything that are going to go to the cafeteria, for instance. 50% is not purchased, so it goes to waste. So that could be probably composted. Out of that, 34% is basically people eat at the cafeteria there, the dining hall, and consumed and disposed. About 8.5% of that is basically food that is not consumed. So again, maybe portion control, we need smaller portions. 51% is to go, so it's quite a bit of packaging that gets done, that gets produced, and again, there's about 9% of food left in this container, so they cannot be recycled, and instead of using them to go to the landfill, we could do something else, right? So the point is that we're trying to reduce our carbon footprint, right? So since our mascot is a bobcat, we have this Shrinking the Paw Print committee that is basically trying to look at waste as part of the equation. So the idea would be to have recycling, so bottles, cans, papers, compost, so one bin for compost, one for paper, one for bottles, and the energy bin that basically is going to be, it's going to have to be sorted out because there's going to be some metal and things like that. But again, part of that can actually be used for energy purposes, right? So in terms of conclusion, we have that waste, in fact, can actually be used for reaching or helping reach the goal of zero net energy at a community, in this case it's a campus. We can use recycling, composting, and energy in terms of, again, a process that converts the waste into energy without using just basically incineration of the waste. And that can allows us to basically reach zero landfill waste. And there's two things that we need to do. One is a detailed experimental analysis of the capacity of the system that we're going to be using in terms of quality of syngas and yield of syngas, and also an optimization of, once we have that analysis and we know pretty well the resources capacity of efficiency, solar, and waste, then when is the best time to use one or the other? All right? So with that, say thanks.
Okay, thank you. Open the floor up